Welcome back. Off we go. We're going to finish today by talking about a couple reactions, or three to be exact, where we reduce alkynes. And then on Monday, we're going to talk about using all the reactions we've learned, the last four in particular, for doing what's called synthesis. So you want to read about that over the weekend. Reduction of alkynes is replacing pi bonds between two carbons with sigma bonds to hydrogen. Hydrogen's less electronegative than carbon, so the electrons are closer to this carbon than they were in the original. Moving electrons closer is reduction. And what I'm trying to depict here with the dollars and pennies is we're increasing the value of this alkyne going this way and kind of wasting our time going to the left. But the one to the left is one we know already, so we'll start there. If you react an alkyne like you did with an alkene with hydrogen and a transition metal such as platinum as a catalyst, then you will generate, using a syn addition, the cis 3-hexene here. And you won't see any of it because that reacts immediately upon formation with another molecule of H2 and the same catalyst as it did in chapter 6 to generate hexane. And hexane is dirt cheap. This is the most expensive way to make hexane you would ever see. Hexane's like a waste product in the petroleum industry. It's little small amounts are found in your gasoline. It's cheap. Okay, so you don't want to try this reaction, but you do want to know how to do this reaction because you've increased the value. Creating double bonds that have geometry is very valuable. And by making exclusively the cis 3-hexene here, you have a very useful synthetic tool. And the discovery of this reaction took many tries. This one kind of reminds me of Edison and the light bulb, going through thousands of different iterations of his idea and finally coming up with one. So the gentleman that did this one was Mr. Lindlar, and he came up with a catalyst that ended up being more reactive than the platinum that he started with, but then he tweaked it. This additive here is just a foundation. It's calcium carbonate as chalk, and he embedded the catalyst, a fine powder version of the catalyst, into the chalk, and he added what's called a poison. Lead 2 sulfate is not only a poison to us, but it's a poison to this reaction, which makes it stop after the first reduction. It no longer has enough reactivity to reduce the cis-alkene to the alkane like we did here. So you have to learn this combination is called Lindlar's catalyst. Please don't do what a lot of students do and forget that hydrogen is not part of Lindlar's catalyst. It's a reactant. Those two H's end up here and here, so they are separate, and Lindlar's catalyst is this combination here. Palladium metal, calcium carbonate, and lead 2 sulfate. It's a syn addition. You don't have to do the mechanism for me, but you do need to know the result and the cause. This is the cause. I could ask for that on a test. This is the result. Separate question. I could ask for this on the test. Now, this is a very expensive catalyst, Lindlar's catalyst, and small schools like ours and other schools typically can't afford that. It would be big industrial corporations that could afford this catalyst, and they do a one-time purchase and use it over and over again. So we need a version that's cheaper. Borine, our old friend from chapter 6, is back. We don't have to put any fancy sec isoamyl groups on it. It's going to react also with acetic acid, both solvent and reagent. And this mechanism doesn't look anything as complicated as the other boron one, does it? So what happens down here is the pi attacks the less electronegative boron, and at the same time we deliver an H to one of the carbons. And because this is an internal alkyne, which I haven't even mentioned, it doesn't matter which carbon you come back to. Our previous alkynes today have been the ones on the end of a chain. Both of these are called terminal alkynes. They're the ones you learned the pKa for, right? Because they also have an H at the end. So terminal alkynes have a pKa of 25. Terminal means they're at the end of a chain. Internal means they're in the middle of a chain. And when they're internal, we don't have to worry about which carbon this arrow comes back to because they're equivalent. And you get a syn addition of H and BH2. It happens 2 more times, which you'll never have to show on a test. And you get each BH reacting just like chapter 6. It happens 3 times. And then this protonolysis step happens. Remember we did it with sulfuric acid and the oxymercuration reaction? We don't need as strong an acid this time. We're going to use acetic acid. And it breaks the sigma. You get a B with 2 R groups. Do not confuse this with bromine, people. That is boron with 2 R groups. These are the R groups here. And acetate, they react and make this. I don't even want you to do that step. That's side product. I don't care. I want you to do this step, though. Show me how that H got on there. And you're going to show me on the next page. Here we go. Sample hydroboration / protonolysis test question. And it has this alkyne. It's internal, and it's in a ring. And it says, by the way, this is the smallest possible ring with an alkyne in it. Why? I guess I can answer that up here. The minimum you need is, I mean, yeah, you need at least these 4 carbons. If you tried to connect them with one more, do you think that's going to work? No. There's way too much room between here and here. You got to span this space with more carbons. And it takes 5 carbons to do that. That's the answer. It takes 5 more carbons to be able to reach from here to here, and the total will now be 9. So the smallest possible ring with an alkyne in it is called cyclononine. Now you've read my book. What was the smallest ring with a transalkene in it? Smallest ring with transalkene. And that was in chapter 5. And you've got to span a slightly smaller gap. That gap compared to, look how far these are from each other. That's a longer distance than these to this. And it takes 1 less carbon. So you need only 4 more. So 4 more. 1, 2, 3, 4. And transcyclooctene was the first time you needed to show trans in the name. That's a review, I hope, for everybody. Cyclononine is the you can't have cyclooctine as a unicorn. It doesn't exist. Cyclohexine is a really weird unicorn, and smaller, weirder. And if you look at the previous page, you attack the B. Here I already have the B with 2 of the R's on it for you. You're welcome. You pick one of the carbons to come back to, and you're halfway through this mechanism. And you have, I could be a terrible cheater here. It's not cheating if the guy that wrote it copies it, right? So I'm just gonna, product looks a lot like that. Yeah. Maybe could have drawn it by now. We don't have a, we put the H on the right, so that'll be a BH2, BR2 right there. R2B. How do you get rid of that and put a proton in its place? It's a very good question. It's called protonolysis. Sigma attacks the H. Acetate leaves. I don't need to see either the boron side product or the acetate side product, so I don't even need to see them or see them react with each other like the textbook has. This is all I need to see for hydroboration protonolysis. One step for the arrows, one step for the intermediate, one step for the arrows. The whole thing's 3 points. Let's not belabor it. So we know 2 ways of making cis alkenes. Can you remind me the 2 ways of making cis alkenes from internal alkynes? The first way was over here. Oh, no, I was at the top of that page. I'm at the bottom. First way was take the internal alkyne, and I guess that's really the first time we saw it. I know it's written below here. React it with H2 and Lindelar's catalyst. That's one way. Or react it with BH3 and acetic acid. That's the other way. Very valuable to be able to make cis alkenes. Do you know what's equally valuable? What's the other kind of alkene? Transalkenes. And here we have a whole new ball game. You don't see this every day. That is not the sodium that you put on your French fries. That'd be sodium chloride, wouldn't it? This is metallic sodium. It is dangerous. This reaction has to take sodium metal, which is stored in a container that has oil in it to prevent air from getting in there. And then you take out the piece of sodium metal and you cut it with a knife. It's a nice soft metal, and use it right away before it starts oxidizing. It wants to react with anything, including oxygen in the air. So you take it out and you react it right away. What do you react it with? Hey, an internal alkyne. What else do you have? Where do the H's come from? We need a source of hydrogens. There's no hydrogens in sodium. They come from ammonia, which serves as both the solvent and a reagent. And I'll tell you more about it. As a reagent, it is a proton source. You say, wow, the pKa is 40. That's not a great proton source. But if you think about what the conjugate, the base it's going to react with is the conjugate base of an alkene. And you say, oh, I don't need a very strong acid for that. This is an incredibly strong base, second strongest base I can think of. So we got to get to that base. So what's happening here? We have a new kind of, this is not an arrow. It looks a little like an arrow. It's curved, but it's only got one half of the head. It's called a hook. Hooks represent the flow of one valence electron. We need that because there isn't 2 valence electrons to start with here. There's only 1. And why does it say radical here? What's that mean? What is a radical? Che Guevara? No, this radical is a species with an unpaired electron. All radicals are species with unpaired electrons. And what's happening there is the unpaired electron is being donated to this carbon. And this carbon says, okay, I can't go beyond my octet. How about I just give up half my pi bond and make a lone pair in the same orbital? And I'll give up the other half pi bond to my partner over there and become a carbon radical. So the species generated here, where you have a lone pair on the right, do the formal charge calculation. It owns 2, 3, 4, 5 electrons. That is an anion. When you're a carbon and you own 5 electrons, you are an anion. And a carbon that owns, let's see, half that, half that, half that is 3, and all of that 1 electron, all of that 1 electron, that's 4. On the periodic table, carbon's got 4. This has no formal charge. So radicals are unstable because they have an octet violation, but they're stable-ish because they don't have a charge. There you go. Octets are not, violations are not great, but at least it's not a cation or an anion, right? And what happens here is this is one of your ammonia molecules right here doing an acid-base step. And here is the radical becoming what? You're giving a radical a new electron, so it's going to be a pair, isn't it? Haven't we seen a pair of electrons? That's an anion. Conjugate base of an alkene, 45. 45 reacts with 40. Sorry. Base reacts with 40 to make 45 every day of the week is what I wanted to say. We're going from 40 to 45. Similarly, 40 to 45. That's a driving force for reactions when the equilibrium in terms of pKa is favorable. Excellent. Let's finish off by doing this mechanism with our molecule down here. Let's try to soak it in so we don't come back here and look at it, and then try to do it down here. And I'll pretend you soaked it in perfectly, of course. So first step was you take that radical, put it on one of the carbons, doesn't matter which one. Then it has to be hooked up. You like that? They get hooked up to become a lone pair. And the other half of the pie goes to the original carbon of the alkyne, the other carbon of the alkyne. Acid base happens with the lone pair because that's the anion. After you have that, you neutralize that. You got your H. You need to make a lone pair on the other one with a second molecule of a second atom of sodium. And then a new base does an acid-base reaction. I think we can do that. You better put the dot on the sodium. Big dot. Oh, that's a lone pair. Sodium does not have a lone pair. It's a unicorn. There's the single radical. And it gets donated to one of the carbons with a hook. And this busts in half and joins up with the hook. And the other half goes to the other carbon. Hook. Don't put arrows there. These are 1 electron at a time. That's a new thing for us. And it's at this time that your cis becomes trans. And you guys don't like drawing rings. Most students don't. I got a tip for you. I need 7 carbons. I'm having trouble with dots. There we go. That's okay. And what do you got? Your rings don't have to look nice. I have a lone pair on the one on the right because that's where I put the second electron. And I have a radical underneath this one here. That's a radical. Which one of those reacts first? Doesn't it make sense that the one that's an anion's more reactive? I hope. And it's the conjugate base of an alkene. And you've got hope I don't have to draw this too many more times. There we go. And what else we got on there? We got an H. Do I have to show the H? No. I got my radical. What has to happen to that? I'm not drawing that again. That's easy to edit that one. It needs to become this so it can do what the other one did. How do we get from there to there? So we can go from there to there. And the answer is it needs another electron. That's not how. That's what. Where does it get it from? Sodium. How? With this hook. With this hook, I thee wet. And now they're a lone pair. And then what happens? We have NH3, molecule number 2. Okay, and how did you get the first one? Was like that. Solvent and reactant. Solvent says it's in huge excess. You don't have to ever write excess with solvent. In fact, you guys never have to write excess at all. The only reason I do is to help jog your memory or mind into remembering that you have to use this more than once. It's to help you. Lone pair grabs H. And if you're keeping score, you made 2 NH2 minuses. Once again, side product, do I really care? No. Those are the conjugate bases of ammonia, aren't they? Every time you took an H off of ammonia, you made one of those. And that's our final reaction. Very important day coming up on Monday. You're going to learn about synthesis and retrosynthesis, which is just thinking about synthesis. And I look forward to that. And I will see you on Monday.
Doctor, just a quick question.
I bet it's a good one. Go ahead.
Yeah. Hopefully. Why would the radical give the carbon that's not charged another electron?
Oh, because that way it gets up to a full octet. So yes, you're doing something bad. Like you said, you're giving it a charge. That's bad. But it's got a full octet. That's good. The combination is still not a happy guy. Okay. It only gets happy at the end when it has full octet, no charges, and bonds that carbon likes to have. 4, right?
Makes sense.
Okay?
Yeah.
All good?
Yeah.
All right. See y'all Monday.